All right, so let's start. So in the last lecture, you learn about heat, okay? And we learned that heat normally transfer from hot body to the cold body, okay? And then you learn about the internal energy, and you know that the internal energy and thermal energy is basically the same thing, and it is the sum of all the energy of all the molecules in a system, okay? And for monoatomic gas, we see that the internal energy is 3/2 nkt, or 3/2 nRT. For diatomic molecule, diatomic gas, it is different. But the important thing here to remember is internal energy or the thermal energy is proportional to the absolute temperature. Okay, so here you see in both cases it is proportional to T, the absolute temperature. Okay, and then you learn about specific heat. Okay, and we see that the heat required to change the temperature of a material is equal to this mc delta T. Here m is the mass of the object, c is the specific heat or the specific heat capacity, and delta T is the change in temperature. Okay, so c is different for different material. Okay, and the table here shows the specific heat or specific heat capacity for different material. Okay, in the last lecture I forgot to tell you that for water the specific heat capacity are this one. Okay, so in some numerical problem we'll be using these, and some student find it confusing that I mean, here you see that ice has one specific heat capacity, liquid water has specific heat capacity which is different than ice, and steam has also another number. Okay, so remember that specific heat capacity for liquid water and the solid ice are different. Okay, normally these two you will be using in some numerical problem. Okay, so for ice, use the specific heat capacity for ice. For liquid water, use 4186. Okay, I don't think we are going to use this one, but yeah, if you use steam in some problem, make sure to use this number, not 4186. Okay, so many student make mistake and they just use 4186 for everything. Okay, but it is not the 4186 not the is not the specific heat capacity for all. Okay, it is only for the liquid water. Okay, for ice, I mean, when the temperature is less than 0°C, we have to use this one, and when the temperature is more than 100°C, then we have to use this one, 2010. Okay, so remember this. And here important convention is Q is positive, I mean the heat is positive when it enters the system, and it is negative when it leaves the system. Okay, and then we learn about the calorimetry, and the important equation for the calorimetry is heat lost is equal to heat gained. Okay, or sum of Q equal to 0, and this is the conservation of energy. And here remember that Q is positive when it enters some system. Okay, and it is negative when it leaves the system. So you have to remember this convention here. Okay, and yeah, it will be more clear when you do some problem. Okay, in the next lecture you will be doing some problem. So the next thing we are going to learn is latent heat. Okay, so when you learn about the specific heat, so let me remind the specific heat equation. So the Q, the heat required to change the temperature of some object, is equal to this, right? This you already see, where m is the mass, c is the specific heat or the specific heat capacity, and delta T is the change in temperature. Okay, so it tells us, this equation tells us that when you add heat to a system, the temperature of the system increases, and when you remove heat from a system, the temperature of the system decreases. Okay, now this is not always true. Okay, so this is not always true. Okay, so when it is not true, this is not true when the system changes its phase. Okay, by phase I mean from solid to liquid, or liquid to solid, or liquid to gas, or gas to liquid. Okay, so during the phase change, they don't change the temperature. You add heat to the system, but there will be no change in the temperature. Okay, so let's see the simulation. Okay, so here, so let's say we have a block of ice at -20°C. Okay, now if you add heat to the system, okay, you will see that between -20°C to 0°C, there will be change in temperature, and that change in temperature, it will be visible in this graph. Okay, in the graph in the right hand side. Okay, and when it is at 0°C, 0°C means the melting point of water, right? Melting point of ice. Okay, so melting point means it changes its phase from solid to liquid. Okay, so at 0°C, because the phase change happen, you will see that there will be no increase in the temperature. Okay, so when all the phase change, when the phase change is complete, okay, then you will see another increase in the temperature. Okay, and then again you will see that there is no change in temperature when it reaches to 100°C, and that's because 100°C means the boiling point. Okay, so at 100°C, liquid water become a gas. Okay, so let's see. So you see that in the graph, the temperature is increasing. Okay, and at 0°C, you see that there is no increase in the temperature. It is it's basically the horizontal. Okay, and then now you see that it's again increasing. Okay, and you will see that at 100°C, there will be another horizontal line. Okay, so you see that you are still adding heat to the system, but there is no change in temperature. Okay, and that's because at 0°C and at 100°C, the phase change is happening. Okay, all right, so let's go back to the slide, and this is the same graph that you see in the simulation. Okay, so here basically it started from -40°C, so -40 to 0, there is increase in temperature, and then at 0°C there is no increase in temperature. Okay, and then so here at 0°C, this is the mixture between water and ice. Okay, and then you see that another increase in temperature between 0° and 100°C. Okay, and then again it's a horizontal line, and that is another phase change. Okay, and here it is the water and steam, the mixture of water and steam. Okay, so you can use MC, I mean Q equal to MC delta T here and here. Okay, Q equal to mc delta T. Yeah, but make sure when you are here, this C is basically the specific heat capacity for ice. And here in this line, this specific heat capacity for water. Okay. And again, here, it is the specific heat capacity for steam. Okay. All right. Now, in this section, we are basically interested to talk more about this line and this line. Okay, the horizontal, two horizontal lines. Okay, so because in this two horizontal line, okay, because in this two horizontal line there is no change in temperature, the Q, the heat you are adding to the system does not depend on the change in temperature. Okay, but what it depends on, it depends on the mass only. Okay, so the Q here depends, I mean, is proportional to the mass of the object. Okay, it is proportional to the mass of the object. Okay, higher the mass, higher the amount of heat it requires. Okay, now if you want to write an equation, then you need a constant of proportionality. Here, this is the constant of proportionality. L is the constant of proportionality. Okay, and this L is different for different horizontal line. Okay, so if it changes phase from solid to liquid, okay, the L will be different than if it changes phase from liquid to gas. Okay, so this L is called heat of either heat of vaporization or the heat of fusion. Okay, so heat of fusion, when the phase change, when the solid changes its phase to liquid, and we call it heat of vaporization. Okay, when it changes its phase from liquid to gas. Okay, so it has two different name. Okay, and you will see in the table. I'm going to talk a little bit more about the table later. Okay, yeah, so here you see the heat of fusion. Okay, when the phase change is between the solid and liquid, and the heat of vaporization when the heat change happen between the liquid and the gas. Okay, so sometimes we also use the subscript F for heat of fusion and subscript V for heat of vaporization. Okay, to differentiate between the heat of fusion and heat of vaporization. Okay, so in this case it will be Q equal to MLF, and in this case it will be Q equal to MLV. Okay, and this heat sometimes we also call the latent heat. Okay, so this LF and LV sometimes we also call it latent heat, or latent heat of fusion and latent heat of vaporization. Okay, so in some numerical problem you probably see heat of fusion, or in some problem you probably see latent heat of fusion. Okay, so do not confuse, if you see latent heat of fusion or just heat of fusion, that means the same thing. Okay, so in this table, we basically need this one. Most of the numerical problem we are going to solve is with water. Okay, so for water, the latent heat of fusion is 333 kilojoule per kilogram. Okay, or for vaporization, 2260 kilojoule per kilogram. So here you see that this is in kilojoule. Okay, so kilojoule is not the standard international unit. So it's basically when you plug this value in the numerical problem, this will be the value you should enter. Okay, joule per kilogram. Okay, and for this one it will be 2260 times 10 to the power 3 joule per kilogram. Okay, so many students make mistake here. They just plug 333. but 333 kilojoule means 333 times 10 to the power 3. Okay, so remember that. Okay, so yeah, the unit, the standard international unit is joule per kilogram. Okay, so you can see it from this equation. Okay, so we see two types of heat transfer. One is the latent heat, and another is regular heat. Okay, so we need latent heat during the phase change. All other time we need just regular heat. Okay, regular heat means Q equal to mc delta T. Okay, and during phase change, we are going to use Q equal to mlv or Q equal to mlf. Okay, all right. The next thing is the heat transfer. Heat transfer method. Okay, so there are three methods by which heat can transfer from one object to another object or one place to another place. Okay, they are conduction, convection, and radiation. Okay, so conduction you already learned little bit earlier. Okay, so this is basically conduction, which you already see earlier. And it tells us that when two objects at two different temperature are in contact with each other, okay, then heat transfer from one object to another object by a method we call it conduction. Okay, and we know already that at some point the equilibrium happen and the temperature of both objects are the same. Okay, so here you see that you already see in the last class this one. Right, so equilibrium happening as time is going on. You see that the hot object's temperature is decreasing and cold object temperature is increasing, and at some point they will have the same temperature. Okay, and this is basically the conduction because they are in contact with each other. Okay, now I am going to talk the mathematical equation for conduction. Okay, so to understand this, let's consider this diagram. Okay, so let's say we have this object. Okay, the cross-sectional area of this object is A. Okay, and let's say that one end of this object is at temperature T1, which is hot temperature, and the other side is at temperature T2, which is cold. Okay, so as you know that heat transfer normally from hot object to the cold object, so the heat will be flowing in this direction. Okay, from the hot side to the cold side. Okay, and let's say the thickness of this object is L. Okay, so I call it thickness because in some numerical problem you will be using, for example, a window. Okay, the glass window. Okay, so for glass window, the length is different than thickness. Okay, and the window's thickness is basically this one. Okay, so so I prefer to say it thickness instead of length. Okay, for example, yeah, so the windows the glass window will be something like this. Okay, so the length is this one and this is the width. Okay, and the thickness is how thick this window glass is. Okay, so that's why I prefer it to say thickness. This length as thickness. Okay, not to confuse when you solve a numerical problem. Okay, now experimentally we found that the rate of heat transfer, so here we are talking about the rate of heat transfer. Okay, so far in the earlier section we use just Q is the heat. Okay, and here Q over T. Okay, so when we talk about the heat transfer method, we are basically interested on the rate of heat transfer. Okay, so that's why it is Q over T, that is the rate of heat transfer. Okay, and when you do when you solve the problem, make sure the unit of rate of heat transfer will be watt. okay, watts. Why? Because it is equal to joule per second, right? Q is the energy, okay, energy is a joule, the unit of energy is joule, and the unit of time is second, okay. Joule per second is the unit for the rate of heat transfer. And you know that in physics 1, you already learned that joule per second is equal to watts, okay. So the energy, the unit of Q over T is either joule per second or watts, okay. Now experimentally we found that the rate of heat transfer is proportional to the cross-sectional area, and it is also proportional to the temperature difference between the two ends, okay, but it is inversely proportional to the thickness, okay. So higher the thickness, lower the heat transfer, okay. Higher the area, higher the heat transfer, higher the temperature difference, higher the rate of heat transfer, okay. Now when you combine these three, you get something like this: Q over T equal to A is this one, and then T1 minus T2 is basically delta T, okay. So here in this equation, delta T means higher temperature minus lower temperature, okay. It is always higher minus lower, okay. This delta T is not the final minus initial, okay. It is higher minus lower temperature, remember that, okay. Again, because it is the temperature difference, you can use either Kelvin or degree Celsius. It will not affect your result, okay. And then you see that in the denominator we have L, okay, the thickness, okay. And we need a proportionality constant, and the proportionality constant here is K, okay. And this proportionality constant we call the thermal conductivity, okay. And in the next slide, I have thermal conductivity. I have a table for thermal conductivity. Okay. Now, here you see that for some object, the thermal conductivity are high. So for example, this object, and for many object, the thermal conductivity are low, very low. Okay. So in numerical problem, we basically use these, okay, although these and these are the same thing, but in two different units. This is not standard international unit, so we are not going to use this line, okay. So the value we are going to use in our numerical problem are the second column, this column, okay. All right. So you see that some objects thermal conductivity is higher and some object is lower, and based on that we divide the object into two different categories, okay. Material with large K are called conductor, and those with small k we call them insulator, okay. So you know that metals are good conductor, good heat conductor, that means their thermal conductivity are higher. Okay, so here in this table you see that silver has 420. Okay, silver is a metal, and it makes sense that the thermal conductivity is higher because it is a metal. Okay, it is a good conductor. Similarly, copper, aluminum, steel. Okay, all right. Now here you see that water is a bad conductor. 0.56 thermal conductivity is 0.56. Okay, all right. Now, even the water is a bad conductor. In water or in air, okay, or in any fluid, okay. So fluid means the object that can flow. I mean, all liquid or all gas, okay, are fluid, okay. So normally gas and liquid are bad conductor, but even they are bad conductor, heat can transfer from one place to another place very effectively in water or in air, okay, but not by conduction method, the another method, and that is the convection method. Okay, so convection, what is the convection method? Convection method, convection occurs when heat flows by the mass movement of the molecules from one place to another place. Okay, So here we have two examples. One is the water and another is the air. Okay, so heat transferring here by the method we call it convection. Okay, so let me explain little bit what happened here in the water, and it's the same thing for air. Okay, so when you turn on the stove, okay, the water molecule close to here at the bottom becomes warmer. Okay, and warmer molecules means they are less dense molecule. Okay, and less dense molecule go up and the denser molecule comes down. Okay, and that's why there is a circulation of the molecule. Okay, and that's because of the difference of the density. Okay, so this circulation continues until all the molecules have the same temperature. Okay, so that's how basically the convection works. Okay, it's the same thing for air. Okay, so in both for convection and conduction, you see that we need a medium. For example, here you see that the molecules are the medium here, and for conduction, the material, this object is the object itself is a medium. Okay, but there is another method we are going to learn now, the radiation. For radiation, we do not need a medium to transfer the heat. Okay, so for example, between the sun and earth there is a lot empty space. Okay, so from the sun to earth this is empty space, nothing in between. Okay, even though sunlight and heat can come from sun to the earth. Okay, and the method by which it comes is called the radiation. Okay, now the rate at which the heat transfer are from the I mean from the sun is proportional to the fourth power of the temperature. Okay, I mean not only for sun, for any object. Okay, so if it radiates and if we know the temperature, we can tell the rate of heat transfer. Okay, and the rate of heat transfer by radiation depends on the fourth power of the temperature of the basically fourth power of the surface temperature. Okay, for example, human body. Okay, so human body has some temperature. For example, the average human body temperature is 37 degrees Celsius. Okay, or in Kelvin it is 273 plus 37, it's is basically 310 Kelvin. Okay, so the rate of heat transfer by radiation from the human body is basically 310 to the power 4. Okay, is the surface temperature. Okay, and it also depends on the surface area. Okay, so the rate of heat transfer here, Q over T, depends on temperature 4. Okay, temperature to the power 4, but it also depends on the surface area of the object. Okay, A is the surface area. And then two other constants. So epsilon is a constant, sigma is a constant. Sigma is a constant that is same for all materials. Okay, so it's called the Stephen-Boltzmann constant, and the value of Stephen-Boltzmann constant is this one. Okay, epsilon is another constant, we call it emissivity. Okay, but it is different for different object. Okay, and its value varies between 0 and 1. Okay, for a black object the value is close to 1, and for shiny object, I mean black or the dark colored object, emissivity is close to 1, and for shiny object or light colored object the emissivity is close to 0. Okay, so when the emissivity is close to 0, that means that object reflect more. Okay, on the other hand, if emissivity is equal to 1 or close to 1, those objects are a good emitter. I mean they emit lot, and at the same time they also absorb lot. Okay, so that's why a good emitter is also called a good absorber, or a good observer is also called a good emitter. Okay. On the other hand, shiny objects are a good reflector. Okay. Now, if the emitting object at temperature, let's say we have an object that is at temperature T1, then the rate of heat transfer for that object is this, right? Q over T, that is equal to epsilon sigma A T1 to the power 4. And let's say this object is surrounded by environment whose temperature is T2. Okay. Now, if T1 and T2 are different, then the emitting object also absorb some radiation from the environment. Okay. And let's say this is the rate of heat transfer that it absorbs from the surrounding. Okay, because the surrounding temperature is T2, it will be absorbing this much of radiation. Okay. Now, because now we have two terms, one is emitting term, another is absorbing term. Okay, the net radiation from the emitting object, the first object that was at temperature T1, will be something like this. Okay, Q over T. This is the same thing. I mean, epsilon sigma A. These are the same for both terms, but then we'll have T1. Okay, and T2, T1 to the power 4 and T2 to the power 4. Okay, and again here, make sure when you solve some numerical problem, you convert T1 and T2 in Kelvin temperature. Okay. All right, so that's it for this chapter. In the next class, I'm going to solve some of the classwork problem. Okay. All right.